pleasure to be here and to talk a little bit about the introduction to climate change. And maybe a third of the talk will be on not all the things we're doing, but some of the things where we need more technology that are perhaps overlooked. All right, so let's see if this works. Is this an automatic? Down is next. Okay. All right. Is this okay? All right. So this picture is to remind you that the life around the world is contained in a very, very thin layer, tens of thousands of feet from sea level, and perhaps at most a couple of kilometers down. But let's move on, and first I want to tell you what's the difference between climate and weather. And the difference is climate is what you expect, and weather is what you get. So that means that climate has somehow averaged in some expectations. And for that, it really means that you talk about climate, and you can't talk about it over a short period of time, let's say 5 years. That's not averaging enough time. You have to average more than 10 or really 20 or 30 years to be sure that it's just not a weather phenomenon. Okay, so let me tell you about how we measure climate. And that's the most important thing, is that temperature seems to be the driver for many, many things. It's temperature and uneven temperature that creates wind. It's temperature that evaporates water, that makes it possible to have precipitation. And it's, of course, temperature that melts things or freezes things, and that could change the sea level. So let's start with more recent measurements of temperature. This is going back to 1850. They usually take 1850 because this is a time when a number of groups around the world began to make direct temperature measurements, i.e. thermometers. And then you might say, well, there's 6 groups measuring the same thing. Does that mean that this is welfare for climate scientists? And the answer is no. It's not. It's pretty subtle because you have to measure and make an estimate of the global temperature, even though the temperature readings are very asymmetric. They are also influenced by the fact that in recent days, especially in the last century, there's heat islanding effects and cities tend to be warmer than the countryside. But given that, many groups have looked at this. I particularly know one group which went with the eye of thinking that all the other people got it wrong because they ignored the heat islanding effects. And then after several years, they said, no, they got it right. So that's part of the way science moves forward. This is another measure of temperature. If you go to Muir, Alaska, and look at 1941, you see a very healthy glacier. You go now 2004 and beyond, you don't see much of a glacier at all. In the United States, there's a park called National Glacier Park. In the next couple of decades, it may run out of its glaciers. So when you're averaging over these decades and you see the glaciers disappearing over several decades, then you say, something is going wrong. What are the main drivers for temperature and climate change? Well, it's obvious the main driver would be the sun. And the sun actually has solar cycles. So these are 3 solar cycles. But notice in this plot here, irradiance is most of the energy we receive from the sun. It's in the form of UV, visible and infrared light. And that annual average is in red. Then there are sunspots, which only contain a teeny tiny amount of the energy, but these are good because sunspots actually are ionizing radiation. Some small fraction make it back to Earth and do something, and then they leave a record of what happened in the rock in the Earth. So whereas there's no temperature that's going to leave a record of what happened hundreds of years ago, ionizing radiation that does something and disturbs the nuclei well. And then there's radio flares and so on. So these sunspot variations tell you that the temperature actually does vary over a period of time. And they, in fact, trigger these El Niños, El Niñas, but not exactly in sync. And so these are ocean things that do vary the weather around the world. Okay. So, as I said before, it's long-term effects. So let's move on and look a little bit further back in time. And so we're going to look back in time. And so we're now going into climate history. The previous slide is to say contemporary times. You might ask, why do we want to go back in history? And the answer is, what happened? I don't know. This is George Santana, an American Argentinian philosopher, and he said, those who can't remember the past are condemned to repeat it. I prefer Gahan Wilson's view of this. So there's a fortune teller asking a very concerned woman, what is she to expect? And the fortune teller says, you will make the same foolish mistakes you have made before. Not only once, but many, many times again. This seems to be true of the human race. In any case, let's move on and look at history. What was the climate like in early history? So now this is going backward. On the right-hand side is the present day within a few years, and you're going back to the year of 1000. And you see that we're rising rapidly in temperature, but there was a little, what's called a little ice age. There's another thing called the medieval warm period, and you don't look, it doesn't look warm because it only happened to be warm in Europe. The rest of the world, it was okay. And before that, it seemed pretty stable. Okay, so how did we measure these temperatures? There were no thermometers. And the way we measure that is taking note of several things. There are tree rings and other measurements of temperature, but the theme now is the temperature varies because the sun activity varies. And it turns out if we take the correlation we see in present day records, then we see a lot of sunspot activity. We have a lot more energy from the sun. And so the sunspot activity that ionizes rocks and leaves a permanent record, you can see going back year 2000 that the sun does vary. And these modern maximums and delta minimums, and then there's something called a Marunder minimum between about 1850 and 1700. That was the medieval cold age. The sun actually was, the sunspots were turning off, but because of the correlation between sunspots and the brightness of the sun was less bright. So that climate change is due to the sun. Okay, let's move on and look further back in history. And the next best records we have are what are called ice core samples, both in Greenland and in Antarctica. The Greenland ones in Vostok went back roughly 400,000 years. The ones in Antarctica, because they have thicker ice sheets, go back 800,000 years and actually now beginning to pass a million. So in this graph, you see on the bottom temperature change. Present day is on the right-hand side going backward 800,000 years. And you also see two prominent greenhouse gases, methane and carbon dioxide. All right? This is where the Neanderthals wandered the Earth. This is where Homo sapiens began to take over. And looking back at this record, you have to honestly say that these poor people had nothing to do with climate change. Okay? These were natural changes in climate. So, a couple of questions. How did we measure the temperature 800,000 years ago? Number one. And I'll take you through briefly, this is a measuring of tree rings, but it also turns out that measuring the ratio of two stable isotopes of oxygen with an atomic weight of 18 protons over the oxygen of 16 protons, turns out to be a very good measure of temperature. Oh, by the way, this is where we are today in 2016, 2019. So we're off the charts, so to speak. All right, so these are tree rings. I don't consider these as good a measure of temperature, but somehow some people do, maybe because they like trees. But if you look at these tree rings, you see very narrow tree rings and you see very broad tree rings. And very narrow tree rings, something has happened. They're typically associated with droughts. And broad ones means that the growing conditions were very good. So, but the good thing about tree rings is it marks a year. Year by year by year, you can see the thickness of these rings. You can make some inference as to what the growing conditions were. These I consider better measurements. You take ice core samples, And you see in the ice core samples, there are stria, these little lines. And those stria actually match up year to year with the tree rings. And so we say, okay, now we have tree rings and we have a suspicion of what the temperature is. And you look at the tree rings in the last 1,000 years, from here to the last 1,000 years, and look at temperature measurements from 1850, and you say, okay, we can get a correlation between what the tree rings are doing or our thermometers are doing. Now we see we can have a correlation between tree rings and these ice stria. So what are you doing? You're measuring something in the core samples, and you're measuring this ratio of oxygen 18 to oxygen 60, and on the x-axis is temperature, and it goes from minus 60 to minus 40, minus 20, 0, plus 20. These are temperatures inferred from conditions around Antarctica, and then this is a ratio of oxygen 18 to oxygen 16. It says percent, but it's actually times 1,000. But you see it's a slightly curved but nearly straight line. And it's this correlation between temperature and the ratios of these isotopes that become a very good measure of temperature. Why are isotopes such a good measure, even though it's a fraction of a percent? It's per degree, and it's because we count the specific atoms using mass spectroscopy, where you ionize the atoms, and the oxygen 18 and oxygen 16 end up in different places. So you're literally counting atoms, and it becomes a very good thermometer. What's the physics behind it? Well, the oxygen 18 is heavier, and so it evaporates less quickly. So if you have a reservoir, let's say in warmer water, there's oxygen 16 and 18. In the water, H2O with now oxygen 18, it's less likely to evaporate than oxygen 16. Similarly, it is more likely to condense. And so it's condensing back into the ocean, but the oxygen 18 fractionally is staying in the atmosphere longer. It drifts over to Antarctica. And so by the time you get into the South Pole, you have a large fraction of oxygen 16 to 18. What happened? Does that mean it's over? Okay. In any case, that makes a great measure of temperature. And the ratio of oxygen 16 to 18 goes well beyond just ice core samples, because a lot of living creatures actually take in oxygen 16, oxygen 18 while they're alive. When they're dead, they stop shuttling back and forth oxygen they get from the environment. So when you die, you kind of freeze in a memory of what your ratio is of oxygen 16, 18. And these are taken, for example, these calcium carbonate shells. The oxygen is now in the carbonate. For those of you who are experts, the delta 18 oxygen is defined by this quantity. It just means that you look at the ratio of oxygen 16 to 18 minus some standard, because there's no absolute standard, and then you adjust the decimal point. But anyway, it's these shell critters that live near the border of land and ocean. Tell us what the sea level was like during that time, because they're living between land and ocean. You've got to do it all over the world because land rises and sinks relative to the ocean. So that's how we make sea level measurements, which is also a part of climate. Let's go back even further in time. You got to pay attention to the time axis. On the right-hand side, the times are going back to 20,000 years. 0, 5, 10, 15, 20 is 20,000 years. And you notice something remarkable. From minus 10,000 years to today, the climate was extraordinarily stable. Before that, it was going up and down between warm periods and ice ages. And it was during that time that agriculture started. And I don't think it was a coincidence, because it did not start in the Fertile Crescent. The Fertile Crescent was one place, but it started in 4 other places around the world within 500 years. When the climate was stable, you can stay there and you can manage to start growing crops. With crops, you have enough wealth, so you can have a social structure, you can have, say, kings or whatever, and most important, you can hire physicists. So now you go in the next period of time, 200, 400, and so on. So those are the Ice Age periods, but you look further back in time, and it was a warm period of time, not because the records were that much worse, As you go back further, it does get worse. But remember, we have these she-shell critters, which were pretty good. By 800,000 years, we were beyond ice cores. And then even further back in time, tens of millions of years, it was very hot. All right, so in the coldest of the ice ages, the United States down to Pennsylvania, Ohio, covered permanently in ice. There's a permanent glacier. This is only 7 degrees centigrade colder than where we are today. So 7 degrees is a profound difference. It doesn't look like much. In Chicago, you can have 40-degree change in one day. But you've got to average over that, and so that you have that. Now, in a warm period of time, the map looked very different. The glaciers are gone. Everywhere they're gone. There's nothing in Greenland and Antarctica. This is an inside joke. You have to be American, and then you have to realize that in America there's politics. If you're a Republican, it's a red. The color is red. And if you're a Democrat, the color is blue. And here you see Florida, which is here. It's underwater. So Florida is a blue state. Anyway, we are not really sure of what the change in the ice ages were. There's a speculation out there by Milankovitch that suggested tiny changes in the Earth's orbit, the eccentricity in the orbit, the tilt of the orbit, and the orbital precession. As the Earth goes around, the axis actually wobbles a bit. And he suggested, if you look at these things, the great thing about these things is it's physics, so you can actually extrapolate back in time with good accuracy. And then you say, are there any correlations? Because you can well imagine, it's not you can actually calculate, that if the Earth's orbit is different, if most of the land mass is in the northern hemisphere, you're going to get changes in how much light gets absorbed versus reflected, things like that. And so there's a suggestion. It's not absolutely ironclad. So again, you can't blame this on the Neanderthals. Again, just to remind you, 7 degrees colder. It was a cold place. But let's continue back on the association with temperature and greenhouse gases. So this is in roughly the present day world, going back to the year 1 in the Christian calendar. So 1 is 1 AD. And you see that the CO2 on this short time scale is very, very flat. But remember, this is part of that long 12,000, 11,000 year climate period. And then you might ask, you've seen all the other records. When the Earth warms up, more methane, more carbon dioxide. And so why is this carbon dioxide different than all the other times when they were very strongly correlated? And so this is what I need to explain to you now. Oops, let me see if I can do this. Aha. This is a complex diagram. It's small print, so I'll walk you through it. Up in the upper atmosphere, we are being bombarded by cosmic rays, typically protons, high-energy protons, mostly from the sun. If a proton hits the upper atmosphere, it can create a neutron. Once you have a neutron, the neutron can actually undergo chemical interactions, nuclear interactions rather, with the atoms in the upper atmosphere, and that neutron can get absorbed by nitrogen-14, and nitrogen-14 then turns into carbon-14. And carbon-14 is a radioactive isotope of carbon, so once it's formed, its clock starts to tick, and after a certain amount of time, half of them are gone. After another amount of time, another half are gone, and so on. This carbon-14 diffuses down the Earth. We eat and breathe and do everything else with carbon-14. We have carbon-14 in us today, so we're radioactive. That's not the only radioactive isotope we have in us. But if we die and we're put in a coffin, the half-life is 5,700 years, but we're in a coffin for 100,000 years. Every 5,700 years, half the carbon-14, then another half, another half, another half. By the time you're 100,000 years, no more carbon-14. Now let's assume that they exhume all of us and put us in a power plant. We're carbon, we're fossilized, good stuff. We create power. The carbon release doesn't have any carbon-14, only carbon-12. It has carbon-13, but we're looking for carbon-14. So that's the idea, that if the material has been sequestered from the environment for 5 or 10 lifetimes, it is no longer radioactive. Okay, so this is, I didn't talk about carbon-13, it's a stable isotope, but let's say with carbon-14, the green is carbon-14, dated from 1750 all the way to the year 2000. This is the CO2 measurements, and the red ones are those oscillations, those are the famous Keeling measurements of CO2 in the atmosphere, and you see the carbon-14s going down, down, down. And you say, well, things stopped. The carbon-14 stopped in 1950, and so what was going on in 1950? 1950, it was the start of atmospheric H-bomb testing. A lot of neutrons. Carbon-14 goes crazy. And so in the atmospheres, the carbon-14 starting around 1960 shoots through the roof. That's the green, is the northern hemisphere. The blue is the southern hemisphere. That carbon-14, made artificially by hydrogen bombs, begins to be absorbed by the ocean, so it's going down, down, down. As it goes down, you see in the northern hemisphere oceans and the southern hemisphere oceans an uptake of the carbon. Since the nuclear tests were done in the northern hemisphere, it takes about a year for the northern hemisphere to mix with the southern hemisphere, its radioactivity. So for those of you who are old as me, you remember a novel and a movie called On the Beach, whereas the people in Australia and New Zealand were the last to die. There's some truth in that. If the nuclear wars started in the northern hemisphere. Then you look down there, and it's still going down, but you say, what's happening? And it turns out the ratio after the oceans have diluted this, the ratio of carbon-14 to carbon-12 still is going down. Why is it going down? Because quantitatively, we have a pretty good estimate of how much carbon we stick up in the air due to burning fossil fuel. Except the fossil fuel we're burning has no carbon-14. So you got a supply up there from neutrons, and you got another supply of no carbon-14 being diluted from fossil fuel, and it dilutes. And it's in quantitative agreement. So this carbon-14 is different, this carbon is different, because looking back, when trees grow and die and everything else, their cycle is hundreds of years, maybe to a few thousand years. You've got to have it sequestered away for 100,000 years. So this is why this carbon is fundamentally different than the previous carbon. And so you look at this carbon and you say, can it change the climate? So that's the smoking gun. Okay, so let's do some more accounting. I'm talking about arithmetic. And so there's the Earth's energy budget. We get virtually all our energy from the sun. There is a little bit of energy in below. In the core of the Earth, it gets very, very hot. It's actually close to the surface temperature of the sun, 5,000 degrees, due to radioactivity made when the Earth was formed, made even before, made by supernova and collapsing neutron stars. But we're concerned about most of the energy coming from the sun, so you have this big yellow thing coming down. And then you have losses. There are some losses reflected by clouds in the atmosphere. There's reflected from the surface. If there's snow, it reflects quite nicely. Light sand reflects quite nicely. Then you have heat energy being reflected from the surface of the Earth, and it gets very complicated because that heat energy is absorbed by the atmosphere. Clouds have a very important role in this, and eventually a lot of that heat energy comes out. So if you average around the world, the outgoing radiation is reduced by gases that trap infrared radiation, therefore less heat escapes. So let me say this again. Heat comes in from the sun, warms up the Earth. The Earth is a warm body, starts radiating heat. Because of the greenhouse gases, it radiates less heat. This is the same effect that if you park your car in the Abu Dhabi sun for a few hours and the sun is out, it gets very hot. Because the sun's rays come in, the car gets heated up, the glass absorbs that heat and it doesn't get re-radiated back. You can do some quick calculations and you find that, first of all, the average temperature around the world, including the North and South Poles, is actually room temperature. Just coincidence. It's about 20 degrees centigrade. And the quick calculation started in the days of Arrhenius and before him, without an atmosphere, you just had a bare rock. The sun coming in, heating up the earth, and then infrared radiation going out. It would be minus, there's minus sign missing, it would be minus 18 degrees. So with greenhouse gases, plus 20, without greenhouse gases, minus 18. I mentioned the biggest uncertainty is due to the clouds. Clouds are both a greenhouse gas, but white clouds also scatter light. And so if you look at the biggest uncertainty in estimating the temperature and climate models are clouds. There's a Goldilocks zone in astrophysics that says we believe that most life can only exist between liquid water and before boiling water. 95 degrees centigrade, if life is based on DNA, DNA unravels. So it's no good. Below freezing, life really stops. You could exist, but it slowed down quite a bit. And that's why we have freezers to store our food. These are the planets that are in this Goldilocks region, but Earth is really smack dab in the middle. Mars used to have an atmosphere, lost it due to cosmic ray bombardment and other things when it lost its magnetic field. Venus, closer, had a big greenhouse gas effect, and so it's quite hot. But Earth is just about perfect. The light hitting Earth is near what we call a black body spectrum. A black body is you take any object, not any object, but a theoretical object, heat it up, and it emits radiation. That's that yellow curve. So the Earth is close to a black body. The other curve is the extraterrestrial solar radiation arriving at Earth, and you see in the ultraviolet, most of that absorbed in the upper atmosphere. But a lot of the energy, more than half, gets hit by Earth, and then you'll notice that there are these notches. I don't think you can't see the notches, but you see it's not a smooth curve. There's some stuff of radiation not hitting the Earth, and so that's due to molecular absorption. So here's another picture of molecular absorption. The sun's rays, black body radiation modified by absorption in the upper atmosphere, and then the upgoing thermal radiation, much colder, so the radiation is much less. The fraction of radiation leaving Earth scales as temperature to the fourth power. So if the surface is, let's say, 0 degrees C, I'll just pick a number, that's 273 Kelvin, which is the right temperature. The surface of the temperature is close to 6,000 degrees Kelvin. The amount of radiation scales as the temperature to the fourth power. So very little energy leaves the Earth, because it's a cold black body. And then now you see total absorption. You see water vapor, carbon dioxide, methane, nitrous oxide. Water vapor is by far the biggest greenhouse gas we have, but we regard water as a follower. When the heat rise temperature, there's more water in the atmosphere, and there's more greenhouse gases, and when the temperature falls, there's less. What is considered the driver are the other gases, carbon dioxide, oxygen, methane. And now you see in this figure in the right middle, there's this big dip somewhere in the middle. That's the CO2 absorption. The CO2 absorption, I believe that's for 450 parts per million CO2. You got a certain amount of CO2 in the atmosphere, absorbs a certain amount. And you see near the bottom of that absorption dip, it's kind of flat. Now I'm going to show you what happens, what's the absorption if it's 300 parts per million, not 400 parts per million. Looks kind of the same. What happens if it's 600 parts per million? If it's 600 parts per million, we're going to be in deep doo-doo. Okay. Looks kind of the same. Who cares about CO2? The absorption is the same. The trouble is, or the good thing is, CO2 is it's absorbed, is completely absorbed. And when you go from 300 to 600, you're just saying that there are more layers of greenhouse gases. So heat from the Earth goes and hits that, saturated. This layer heats up, radiates out, goes to another layer, radiates up, radiates out. And you'll go to more layers, And the last layer, which is the connection to space, is a little colder. So it gives out a little less energy. But you see it's a second order effect. Okay, so CO2 is saturated. Methane and nitrous oxide are not. You double that, you double the absorption. And so that's why those gases count for a lot more. So here we have the three major greenhouse gases that we have to contend with. Again, going from year 0 AD to 2000, CO2 is in red, methane is in green, and N2O is in blue. What I just explained is because CO2 is saturated, you can compare us to the other gases, methane and nitrous oxide, and methane is considered 84 times worse. It's considered 80 times worse because eventually methane degrades in a couple of decades to CO2 in the upper atmosphere. Bombardment and it oxidizes. So it becomes CO2, so its effectiveness becomes 1 like CO2. Nitrous oxide a bit more stable, so it stays up in the atmosphere 300 times longer. And because of that, even a smaller concentration of nitrous oxide is a big deal. And so whether you do 30-year averages, 100-year averages, or something else, there would be a carbon dioxide equivalent. So, and it's fully in the lifetimes. Okay, so that's the climate. This is measurements. There's a greenhouse gas effect for sure. What's the problem? So I've actually got the bigger numbers. This is radiation, 340 watts per square centimeter going in. Look at all the stuff going out. And the net absorbed energy on the Earth is 0.6 watts. Okay, out of 340, the difference is of doing greenhouse gas is 0.6. So this change is teeny tiny. And so that's the problem. Nevertheless, climate models have got it pretty good. So here is in the last IPCC summary report, the physical basis model. You see if there was only simulated solar volcanic, the temperature, including the oscillations in the brightness of the sun were included. You should not have seen any temperature change, and the observed ones are in black, and the brown is a simulation based on how much CO2, methane, nitrous oxide, and other greenhouse gases like freons. And so the width of these bars is the uncertainty associated with the IPCC. Looks pretty good. There's a problem. If you do an ab initio simulation using humongous supercomputers, it doesn't really tell the effect because those runs tend to go unstable. They're too sensitive. And it's going along, and all of a sudden, the temperature goes up or it goes down. So they have to be somewhat hand-tuned. And so that's why they're not to be completely fully trusted. They're getting much better over the last couple decades, but anyway. So let me recount the history. In this diagram at the right, the 2 degrees, we see this little circle we call stabilized Earth. That means the last 10,000 years we had stable climate. And that's why we have so many kings and physicists. But before, we were oscillating back and forth between the ice ages. But there's something else that could occur based on the climate record. You can go into a very hot period. Remember, going back further, it was stable. So that means there's no thermostat that keeps us in this wonderful period we happen to be in today. In fact, it's an unusual period. It's either way hotter or oscillating between around today and way cold. Way is 5 degrees, 6 degrees. So Hans Schellenhuber, a climate scientist, said, well, we're in this little peculiar stable region where you're looking back in time and the Earth is in this stable region, and we're approaching a fork in the road. We either can go into the very hot cycles that we've observed tens of millions of years ago, millions of years ago, or maybe we can go back to the stabilized. We were going to the ice age before we started emitting greenhouse gases. I met Hans about 5 or 6 years ago. He's beaming. We're both in the Pontifical Academy of Sciences, and he says, Steve, I've proven we're going to avoid a new ice age. So I said to Hans, tell me something I don't know. But if there were no humans, we would have got into a new ice age. Slowly, very slowly. Okay, so these are the projections of what we have going from 1990 and the projections to 2021. This graph was made around 2015 or something. And during this period, if you look back, to remind you, when the last interglacial, the Earth was about 2.5 degrees warmer than before the Industrial Revolution. But we're 1.2 degrees. So we're really got 1.3 degrees more to where we were in the warm period, where there was a fossil record. But because there was fossil record, we know what the sea level was. The great thing about the fossil record and temperature is you don't have to do a computer calculation. It's history. And the sea level was 6 to 9 meters higher, 1.3 degrees warmer than today. So, there's something else I need to tell you. The real effects of climate change, of what we've done to the greenhouse gas effect, won't be seen for 50 years or more, 50 to 100 years. Why? If you've ever swum in the ocean, by the time you're going a few meters down, the water's getting cold very fast. And in the bottoms of the oceans, 2-3 kilometers down, it's very close to freezing. And the mixing time of the top of the ocean, which is pretty warm, and the bottom of the ocean is very long. Over the last couple of decades, we're beginning to make detailed measurements using things that measure salinity and temperature. There's 5,000 of them all around the globe in 1 degree swatches. They go up and down. They come up to the surface. They phone home, a GPS satellite radio, and they go back down again. And we measure the mixing time. It's slow. And it's like ice cubes in a glass of water. Until those ice cubes melt, the place stays cold. Because the bottoms of the ocean are very cold, until you dump all the heat into the ocean to warm it up, the surface stays cooler. And it takes about 50, maybe 80 years. So I say it's like cigarette smoking because you smoke 30 or 40 years ago, you begin to incur mutations. You may decide 20 years ago you stopped smoking, but you're now incurred these mutations. It's multiple mutations that give you the heart disease, the stroke, the lung cancer. And then way back late, 50 years from now, you get lung cancer or something like that, even though you stopped smoking 20 years ago, because it was baked in. And so, is climate change baked in? And the answer is no. It can be reversible, but it's only reversible if you get rid of the greenhouse gases. Okay? So, anyway, we're here now. We're here from business as usual and current policies. Current policies are saying that we'll end up 2.8 to 3.2 degrees centigrade, roughly 3 degrees centigrade, but we're worse than current policies. And the 2 degrees and 1.5 degrees are much more aggressive in the light blue and other blue. The y-axis is what you have to pay attention to. That's the total emission per year of carbon, and it starts at 0. And so by the end of this century, we have to be negative. That means all the carbon emission from all the greenhouse gases we throw up actually has to go below 0. And that is a problem. And I'll talk a little bit more about that. This is our world in data of the greenhouse gas emissions. See that little dip? And then it went back up. That was COVID. It slowed up the economy, travel, lots of things. Okay. So here's a graph. Started beginning of Industrial Revolution, going to 2022. Cumulative emissions. Why cumulative? Because when you emit carbon in the atmosphere, within a year or two, it gets absorbed by the oceans and land, grows more vegetation, but it's a cycle. So it goes up and down. It cycles yearly. The reason the Keeling curve had those oscillations is there's more vegetation in the northern hemisphere than the southern hemisphere. So due to photosynthesis, you're actually capturing carbon out of the atmosphere due to plants, but in wintertime, you're giving it back. The falls leave, they rot, and then they give back carbon dioxide. Cumulative because even though it's cycling, if you have it at a certain level, how long will it take to go down to another level? That carbon dioxide will cycle between land and ocean for hundreds to tens of thousands of years. There's large error bars, large debates, whether it's 1,000 years, 10,000 years, or longer. But for 1,000, 10,000 years, for all we're concerned, that's a long time. So there's an old saying that if you don't change direction, you'll end up where you're heading. That dotted line is the 2-degree mark. We will pass that in probably 15 years. So 2 degrees is no longer an option. All right. I want to point out 80% of greenhouse gas emissions occurred since 1950. Okay, the weather is changing. These are one-time events, so this is weather, not climate. This is a satellite image. I don't know if it shows it better. No, it doesn't show it better. Of the United States, Northern California, we were hit with what's called an atmospheric river. It's a new term that's emerged in the last 5 years, where suddenly people are, where they live, they could see 10 inches of rain within a few hours. It's as if one took a whole bucket and just dumped it down, and then you see incredible flash floods. It's these atmospheric rivers, or these cold spells, these hot spells, these things, the hurricanes, which are called extreme events, and it's the extreme events that are causing most of the damage. And so I, over a period of 7 or 8 years, with Shahil Sonoy, who is a graduate student of mine, Kevin Trentberth, who's one of the most published and respected climate scientists around the world, he was, to keep us honest, we were doing applied math in a field called extreme value theory, to look only at statistics to say, what are we doing? What's happening? No climate models, just statistics. And the answer is, we found something that other climate models know. The probability of an extreme event does not go like a Gaussian. As a Gaussian goes like e to the minus x squared over sigma squared. The tails drop off very rapidly. In extreme events, the tails drop off either as linear e to the minus x times a constant, or the e to the log of that. And what we say is that the extreme events have very long tails. And the long tails mean you can have an extreme event as well. And so the real question is, can we get any closer to doing this? It's hard, especially because of precipitation, because precipitation is a rare event. So let me go back. I'm going to talk how much time do I have? 10 minutes. Okay, here's some needed innovations. First, there were unintended consequences to the multiple industrial agricultural revolutions, and notably CO2, methane, nitrous oxide, fluorinated gases. It turns out that half of the methane and 3/4 of the nitrous oxide is due to food production and food waste. There was a third agricultural revolution. It started with the invention of the ability to make nitrogen-based fertilizers from nitrogen we find in the air. It's called the Haber-Bosch process. For that, Haber got a Nobel Prize in 2018, and they gave one to Bosch in 2031 for the invention he did with Haber in 2016. So 2 Nobel Prizes for the ability to grow more food. Another Nobel Prize for the ability to grow more food to Norman Borlaug, who made cross strains of wheat that could grow in heavier fertilizer and much more productive, not just in developed countries, but he was actually living in developing countries, Mexico and South Asia. Okay, so there you have that. This is how profound the agricultural revolution was. From 1960 to 2016, the population of the world goes from 3 billion to 7.4 billion. Land under cereal production for grains, wheat, corn, rice, those things, flat. Population production per unit area grew 3.5 times. That's a pretty good revolution. Okay, if it wasn't for this, we would not be able to feed 8 billion people. But we need a third and fourth agricultural and industrial revolution. And that revolution means we've got to get rid of these greenhouse gases that are still rising. And so you've heard about all the wonderful ideas of solar and wind and other sources of renewable energy. And it is absolutely true, the so-called levelized costs, if you include the investment costs, the maintenance costs, and the no more fuel costs, they're actually going below the cost of natural gas in most places in the world. But when you're 10% of the energy production, it doesn't matter. When you're 50, 80%, it matters a lot because you need huge backup systems. And you've also got to decarbonize all the materials we use, the steel, the cement, the chemicals, and other things. All right, world has lots of sun. Where you see red, lots of sun. Great, but there, where you see yellow and green, not much sun. And so you've got to get the energy from where the sun is to where it's not. Here you see on the right-hand side, high voltage DC transmission lines. You can transmit electricity most efficiently with high voltage DC. And you see these linkages planned by Europe. They want to actually include Iceland. They want to include Scandinavia, especially Norway, because it has lots of hydroelectric dams. So you can pump water up and down between dams. And that's the world's best battery. And Iceland is huge geothermal and precipitation. Point out that Northern Africa is pretty good. Middle East is pretty good. People are beginning to make toy plans, academic plans, to link where the sun is good, where there are not that many people, to where the bigger markets are, also with DC lines. But you need transmission lines. This is a 1.1 million volt transmission line. Those little things that you see there, those are people. And the thing is a standoff. Okay, these lines carry 12 billion watts of energy. Over 2,300 kilometers, they lose 5% of the energy because the voltage is so high. And so, so going to better high voltage lines is an essential part of what we need. That's a transformer. Those little things down below are people. Okay, it's expensive, but it's actually, turns out, compared to lower voltage, to be comparable because you're sending 12 gigawatts, not one. All right, let's move on. The wires we use for the high voltage lines are actually aluminum, and then inside the aluminum there's a core of steel. The steel is there to keep the lines from sagging. So the steel is only there for physical strength. But you see there's spaces in the aluminum, so in the new lines you fill up all the spaces and you anneal the aluminum, so it's softer, so the crystalline structure is better, so it conducts better, but it's softer. And then you use a carbon composite. Now there's been a bit of a breakthrough. You can take methane and you can turn it into carbon fiber. And Matteo Pasquale at Rice University has been doing this for about 15 years. Turns out he started funding through Shell, Royal Dutch Shell, and 5 years before that, I suggested, I was an advisor to Shell and said, you know what, you got a lot of methane, you got a lot of oil. If you can take methane and convert it to carbon fiber, and it can start to replace structural things and other things, then it doesn't go into the atmosphere and it's useful. So he gets funded, and over the last 16 years, he starts making carbon fiber that's both strong, on the strength is on the y-axis, and conductivity is on the x-axis, and his carbon fiber is now better than steel and approaching aluminum and copper. The theoretical for nanotubes of the carbon is actually 1,000 times better than copper or aluminum. The real issue is you get close to carbon fiber, get to copper and aluminum, it's got to be as cheap as copper or aluminum. And that's an issue, but we're heading there. Another point, renewable energy, asymmetrically distributed. If you can take energy, green energy, sun, wind, other things, liquefy it, put it on a tanker, and ship it anywhere around the world, that's better than a transmission line, much cheaper than a transmission line. And to drive this home, if you take crude oil and ship it from, let's say, the Middle East to Japan, and how much does that transportation cost in the price of gasoline in Japan? It's 2 cents. Transmission in a liquid on a supertanker costs virtually nothing. And so that's the deal. You can make hydrogen, you can make methane, green hydrogen, green methane, liquefy it in some form, ammonia, liquid nitrogen is too cold, and ship it on a tanker. Then you can distribute, export the energy. Batteries, chemical batteries. We'll start with EVs. plotting here energy per unit weight on the x-axis, energy per unit volume on the y-axis. This is where batteries will be 15 years from today. That's not speculation. I'm on the board of directors of a battery company. I do battery research myself. We're sending out samples over there now, which means 10 years from today, they will find their way into cars. Okay. The cost of batteries is plunging. On the x-axis, every time you go by 1 notch, you're increasing the deployment by 1 order of magnitude. On the y-axis is the cost of the batteries, but it's on a log scale. And this is called the learning curve. And once you start producing enough, you get on this learning curve. So after 2000, you're making a lot of batteries. You're on a learning curve, and went from 2000 to 5 minutes. 1 minute. Okay. Anyway, I'm going to skip all the great stuff I'm doing in batteries. You didn't want to hear that. I'm just going to move on to just, nuclear. Nuclear is good. Why do I think nuclear is good? Because these are the deaths per unit area from brown coal. Where's nuclear? Nuclear is down here. It's between wind and solar. Using nuclear power, there are more people that die from hydropower and burning wood pellets and natural gas than nuclear. Hundreds of times more because of the air pollution issues. Fukushima, it turns out that the radioactivity being released in Fukushima is 10,000 times higher than if you were eating fish 4 times a week just caught off the site where they're dumping the radioactivity than eating 1 cup of bok choy. There's an irrational fear of this. Okay. And we need to capture carbon dioxide. The goal, we don't have this technology. It's got to drop by factors of 2 or 3. And remember, we're emitting 52 gigatons of carbon dioxide equivalent a year. But some of this stuff, food production, fertilizer, we don't know a way of getting rid of fertilizer, which is one of the worst greenhouse gases. So for the next couple of decades, it will be a problem. Photosynthesis captures 20,000 tons of carbon dioxide a year, and so it may be the best carbon capture. But I'm going to end. How long does it take to make a transition to net greenhouse gas? So look at history. We went from wood to coal. You look at the time it took, maybe 75 years. Then we go from coal to petroleum and natural gas, 65 years. So you say, it's going to take 65 years. Where have we started? Well, we just started. Renewables is a little green sliver, maybe 20 years, okay? So maybe another 40 years. It's worse than that. That's fraction. This is actual amount of energy used. We never transitioned away from coal or oil or nuclear gas. We just added more sources of energy. So until that energy becomes green, we got a real problem. So you think it's going to take 65 years to make a transition? No. You got to dump all the rest of this stuff. We haven't dumped the rest of this stuff. So we're still currently on a collision path of greater than 3 degrees centigrade. Okay? Whether it's 3 or 4, we think 2 is disaster. So think of the movie The Titanic. We're nearly full speed ahead, blindly going into the dark, and we're still heading to the iceberg. Thank you.